Okay, very good afternoon to all of you. Am I audible?
Good afternoon, sir. Yes, sir.
Okay. So in last few classes, we have discussed about, or rather, we have derived the Maxwell's four equations, but that was basically due to the static electric field and magnetic field. Now, and today we'll discuss that is what will be the modifications in the Maxwell's equations for the time varying electric field and magnetic field. So basically, you have to consider the modifications in the Maxwell's equations due to the time varying electric field and magnetic field. On this basis, first we'll discuss about the resultant force on a charge due to the on a moving charge due to the electric field and magnetic field, and that is basically explained by the Lorentz. So we'll first discuss about the Lorentz force equation. After that, we'll discuss about the boundary conditions based on the magnetic field. Then we'll discuss about the Faraday's law that describes the induced magnetic field due to the change in electric flux. And we will discuss the corresponding modification in the Maxwell's equations. After that, we will discuss about the continuity equation, that is the current continuity equation for the time varying field. And due to these modifications of Ampere's law, what will be the change in the Maxwell's equations that will be discussed. So I'm going to share the today's presentation. Is the PPT visible from your end?
Yes, sir. Yes, sir.
Okay. Slideshow. So first we are going to discuss about the force due to electric and magnetic field on a moving charge, and that is basically described by the Lorentz force equations. So first we will consider the force on a charge. So this Lorentz basically explained the resultant force acting on a moving charge due to electric field and magnetic field. So first we'll consider the force on a moving charge due to the electric field. That is force acting on a moving charge due to electric field. Now, so we are considering a uniform electric field that is along the x-axis, and under this electric field there is a moving charge q that is moving with a velocity of v. So what will be the force? That is force due to the electric field, that is F of E, that will be equal to the product of the charge and the electric field. So we are considering a moving charge that is moving with a velocity of v under the uniform electric field E. So as per the Lorentz force, or as per the Lorentz explanation, the force on this particular moving charge due to the electric field, that will be equal to Q into E. Now the question is whether what should be the direction of this force. We are already familiar with this particular point. If the charge is positive, if the charge is positive, then the direction of force will be in the direction of electric field. If charge is positive, then the direction of force will be in the same direction of the electric field as in this particular drawing. But if the corresponding charge is negative, then the direction of force will be in the opposite direction of the electric field. That's about the force on a moving charge due to electric field. Next, we will discuss about the force on a moving charge due to the magnetic field. So once again, we have considered a moving charge Q that is moving with a velocity of v under the electric field. This is the uniform electric field. Sorry, uniform magnetic field B. So this particular charge that is moving with a velocity of v under the uniform magnetic field intensity B. So if this is the vector B, direction of magnetic field V, and this is the direction of velocity V, then you can find out the direction of force on this particular charge due to the magnetic field according to the right hand thumb rule. So the direction of force will be the cross product of these two, V cross B, and as per the Lorentz equation, the force due to the magnetic field, that is the force on the moving charge Q due to the magnetic field B, that will be equal to Q into the V cross B. So you can find out the direction of this force due to magnetic field by the right hand thumb rule. It is equal to Q into V cross B. So what will be the resultant force? So the resultant force will be the sum of these two force due to electric field and force due to magnetic field. So if we sum up these two force, it will be ultimately F equal to Q into within bracket E plus V cross B. Q into E plus V cross B. So that will be within the first bracket. And that particular equation is known as the Lorentz force equations. Clear? So Lorentz force equation basically describes the force on a moving charge that is moving with a velocity of v, and that is the total force. One is force due to electric field and another is the force due to magnetic field. Now, what is the applications of this Lorentz force equation? That is very important in this electricity magnetism. With this particular Lorentz force equation, you can easily determine the orbits of the electron in a magnetrons. You can find out the paths of the proton in cyclotrons. Also, you can determine the plasma characteristics in a magnetohydrodynamic generator. And you can also determine the motional characteristics of a charged body under the influence of electric and magnetic field. So these are the different applications of the Lorentz force in the electricity magnetism. You can easily determine the orbits of the electron in a magnetron. You can determine the paths of the proton in a cyclotrons. You can also determine the plasma characteristics in magnetohydrodynamic generator. And by applying this Lorentz force equation, you can also find out the motional characteristics of any charged body under the influence of electric and magnetic fields. So that's all about the Lorentz force equations. So next we are moving to discuss about the magnetic boundary conditions. We are already familiar with the electric boundary conditions. Similarly, now we have discussed about the magnetic boundary conditions. Basically, when a magnetic field enters from one medium to other medium, there may be some discontinuity in the magnetic field, which can be understood by these magnetic boundary conditions. So we are going to discuss about the magnetic boundary conditions basically to determine the discontinuity in the magnetic field when this magnetic field traveling from one medium to another medium. Is it clear? Magnetic boundary conditions will describe us
Yes, sir.
whether is there any discontinuity in the magnetic field due to the change in medium or when magnetic field traveling from one medium to another medium. As you know, in case of boundary conditions for the electric field, we have to deal with the two component. Suppose in that case there are two mediums that is separated by this line, medium 1, medium 2. That is the so this particular line is representing the interface between two medium 1 and medium 2. And if we consider the magnetic field on the both medium, so we have to deal with two component. One is Bt and Bn. One is normal component, another is tangential component. Okay, so in each medium we have to deal with the normal component and tangential component. I am not going to discuss what is normal component, what is tangential component, because I think we have discussed in details about the normal component, that is the component that is perpendicular to this interface, and tangential means that is in parallel to the interface of these two medium. So to determine the boundary conditions for the magnetic field, we have to find out the boundary conditions for normal component. That is, what will be the change in normal component due to the movement from one medium to another medium. After that, we will determine what will be the change in tangential component due to the movement of magnetic field from one medium to another medium. So first we will consider about the normal component of the magnetic field. So to discuss about the normal component of the magnetic field, in same way we are considering this is the medium 1, this is the medium 2. These two medium are separated by this particular surface that is drawn in blue line. So this is the interfacing surface between the two medium. Now we are considering that, and obviously this is the x-axis, this is the y-axis, and this is the z-axis. Now we are considering that the magnetic field is traveling from medium 2 to medium 1. We are considering that the magnetic field is traveling from medium 2, that is the corresponding normal component is Bn2, and it is traveling towards the medium 1, where the normal component is B of N1. Now to determine the relation between these two normal components, that is the Bn1 and Bn2, we are considering a differential volume. We are considering a differential volume on this particular surface. This differential volume with the side of del y, del x, and del z. As we are considering it as an elementary volume with very infinite, very small thickness, so we can consider that this del z is tends to 0. So before that, with this particular surface or with this particular volume, you can find out total 6 surfaces: left surface, right surface, top, bottom, and this front surface and the back surface. Like same thing we have discussed in the during the discussion of boundary conditions for the magnetic field. We have on the interface of the two medium, we have considered a very small elementary volume with a very small thickness. That's why we have considered del z is tends to 0. Now in this elementary volume, there will be total 6 surfaces: top, bottom, front, back, and left, right. So on these 6 surfaces, now we have to determine what should be the magnetic normal components. So once again, you have to take the help of Gauss's law for magnetic field. As per the Gauss's law, we know that the total line integral of B dot ds, that will be equal to 0. As per the Gauss's law, the total flux leaving a particular surface, that will be 0. So now there are total 6 surfaces. So we have to consider the integration of 6 surfaces separately. B dot ds for the top surface, B dot ds for the bottom surface, B dot ds for the left, B dot ds for the right, and B dot ds for the front, and B dot ds for the back. Now once we consider that del z tends to 0, okay, I am moving to the previous slide again. When we are considering del z tends to 0, that means the front surface, that is this particular rectangle, this front surface and the back surface, similarly the left surface and this right surface, this particular rectangle, their area becomes 0 as del z tends to 0. So only you have to consider the two surface, one is top surface, another is the bottom surface. So that's why this 4 integration will be 0. Now on this top surface is representing that is the normal. On the top surface, the normal component is b of n1. What about the ds? ds is nothing but the del x into del y. Now coming to the b dot ds on the bottom surface. B dot ds on the bottom surface. On the bottom surface, the normal component is b of n2. The area is del x into del y. Why this negative sign is considering? Why this particular negative sign is considering? Tell me why this negative sign is considering. See, this in case of top surface, B1 is leaving the top surface. In case of bottom surface, this Bn2, that is entering into the surface. Okay, so that's why these two will be with opposite polarity, opposite sign. So by the simplification of this equation, we find that Bn1 equal to Bn2. That means if the magnetic field travels from one medium to another medium, there will be no change in the magnetic field. Sorry, there will be no change in the normal component of the magnetic field. Okay, but if we consider the magnetic field strength, that is H1, Bn1, Bn2, this is representing the magnetic field, or you can say the magnetic field intensity, a magnetic flux density. They are remain same when magnetic field passing from one medium to another medium. But what will be the relation between the magnetic field intensity? That will be the ratio of to permeability. So on B, we know the relation between B and H. B equal to mu H. So Bn1 equal to mu1 into H1n, and Bn2 equal to mu2 into H2n. So if you find out the relation H1n by H2n equal to mu2 by mu1. So what will be your conclusion? In case of magnetic field, the normal component of the magnetic field or the magnetic flux density, they will remain same when magnetic field travel from one medium to another medium. However, whatever their magnetic field intensity will be the ratio of permeability of the two medium. Sorry. So that's about the normal component. The rest of the things, that is, we have to now consider the tangential component. So what should be the modification in the tangential components due to the change in medium? So now once again we have considered the two medium 1 and medium 2. They are separated by this particular interface or surface. Now the tangential component means Ht1, that is the tangential component in medium 1, that is Ht2, that is the tangential component in medium 2. They are in parallel with the interface of the two medium. That's why they are tangential component. Now this is x-axis, This is along x-axis and this is along y-axis. So now we have to consider a closed loop. Now we have to consider a closed loop that is formed by this particular, we can say that is by square A, B, C, D, this square. This closed loop we have to consider. So which particular law we have to apply now to find out the tangential component? Instead of surface, now we are considering a closed loop. As in previous case, we have considered the closed surface. That's why we have to apply the Gauss's law. But now we are considering the closed loop. So which particular law we have to apply to find out the relation between the tangential components? No answer. Now we have to apply the Ampere's law. Now we know that as per the Ampere's law, what will be the line integral of magnetic field intensity H, that is H dot dl. H dot dl equal to I enclosed as per the Ampere's law. You have to follow the class, otherwise you will not understand today's class also. As per the Ampere's law, if we consider a closed loop around a particular conductor that is carrying a current I, that's we have discussed in the last class. So what will be the induced magnetic field? Magnetic field intensity H dot dl equal to, that is the enclosed current enclosed in the corresponding loop. Okay, so that is the Ampere circuit law. H dot dl equal to I enclosed. Now I enclosed, how you can replace this I enclosed in that case? Now that is K into del X. K into del X. K into del X, because this tangential component is along x-axis. So if we consider this AB equal to del X, BC equal to, we can consider that is del Y. So similarly CD will be also del X. Now we are considering a parameter K, that is K is known as the surface current per unit length. If K is the surface current per unit length, then what will be the total current enclosed by this particular closed loop? That will be K into del X. Now in this particular integration H dot dl, we consider these four paths, A to B, B to C, C to D, and D to A. So integration of H dot dl over A to B, integration of H dot dl over B to C. In that way, we have considered four different integrations. Now, over A to B, over this particular path, A to B, the tangential component is in parallel. So it will be, there is a tangential component, so it will be H1 into del X. What about the second? That is H dot dl over B to C. Over B to C, there is no tangential component. Along this particular line, along this particular B to C, there is no tangential component, so it will be 0. Next, what about this C to D? C to D again, C to D, there is another tangential component HT2. HT2 is there, and the length is del X, so it will be HT2 into del X, but there will be a negative sign because the direction of C to D and H to T are opposite of each other, so there will be a negative sign. Is it clear? We are moving from point C to D, but the tangential component is from left to right, so there will be a negative sign. Next, about this last line from D to A, if you integrate from D to A, there is no tangential component, so it will be 0. So finally we got HT1 into del X minus HT2 into del X equal to K into del X. From both sides of the equation, del X will be cancelled out. So finally we got Ht1 minus Ht2 equal to K, where K is the surface current per unit length. That means in case of magnetic field, if we consider the magnetic tangential component of the magnetic field intensity, the difference between the two tangential component will be equal to the surface current per unit length. They are not equal. That is Ht1 not equal to Ht2, like the normal component. Unlike the normal component, Ht1 is not equal to the Ht2. Now this is the relation of tangential component or boundary condition for the tangential component when the magnetic field is traveling from medium 2 to 1. Medium 2 to 1. This particular relation is valid when the magnetic field is traveling from medium 2 to 1 that we have mentioned in the previous slide. So if the corresponding magnetic field travels from medium 1 to 2, then what will be the modification in the equation? If it travels from 1 to 2, it's moving from 2 to 1. That's why it is 2 1 minus T1 minus T2, Ht1 minus Ht2. So if it moves from 1 to 2, then it will be Ht2 minus Ht1 equal to K. That thing you should remember. This particular equation is valid when the magnetic field is traveling from medium 2 to medium 1. If you consider that the magnetic field is traveling from 1 to 2, then it will be the difference. It will be different. That will be Ht2 minus Ht1 equal to K. The main thing is that the tangential components are not equal. There should be a discontinuity if magnetic field travels from one medium to another medium. Now with this discussion about the boundary conditions related to the magnetic field, we will consider one example, then it will be more clear. This particular magnetic field H1 is given, H1 equal to 4Ix plus 6 IUI plus 2 IZ. Then you have to find out the H2. The problem description is given. Two medium 1 and medium 2. Medium 1 and medium 2, they are separated by a surface where the current per unit length, that is the surface current per unit length, that is equal to K is given, K equal to 2Ix plus 4Iz, and the magnetic field moving from medium 1 to medium 2. You should remember that the magnetic field in this particular example, magnetic field is moving from medium 1 to medium 2, and in the medium 1 the corresponding magnetic field is given, and this magnetic field is moving along which direction? Along x direction. And this is the x, that is this interface of these two medium is in parallel with the x-axis. And what about the z-axis? As per our previous discussion, what about this z-axis? This symbol indicates that the z-axis is out of the page, okay, which is perpendicular to the x and y. So on this particular surface, x is with this particular surface, interfacing surface, x is in parallel and z is perpendicular. So first of all, you have to determine what will be the direction of normal component and what will be the direction of tangential component. Tell me. we are considering the two medium 1 and 2. They are separated by a particular surface where the surface integral surface current is given k equal to 2ix plus 4iz. Now magnetic field is moving from medium 1 to medium 2. In medium 1 mu1 is 2, in medium 2 mu2 is 4. Then you have to determine the h2. That means basically you have to determine the tangential component and the normal component of the magnetic field in medium 2. In the medium 1, all the components are given. Depending on that and depending on the relations between depending on the boundary conditions, for the magnetic field, you have to determine the field in medium 2, magnetic field in medium 2. Tell me, what is the normal component? Normal means that she is the perpendicular to the interfacing surface. So what should be the direction of normal component? Please tell me, anyone from your side. Am I audible? Yes, the normal component should be along y-axis. This is the surface of interface or interfacing surface between two medium. So normal component means they are perpendicular to this particular interfacing surface. What about the tangential component?
Along x.
Not only along x, they may also be in the z direction.
Yes, sir.
Okay, so that is very important to determine first. So the normal component means that is the component along the y-axis, and the tangential component means that is the components of the magnetic field that are in the x and z direction. So in this particular given magnetic field, this is the x component, this is the y component, and this is the z component. Now normal component is along y-axis. Okay, so first we will determine the normal component. As per our previous discussion about the boundary condition, we know that what is the relation between Bn1 and Bn2? Bn1 equal to Bn2. Bn1 equal to Bn2 means that is the basically mu1 into H1, Hn1, that is equal to mu2 into Hn2. And what about the tangential component? If it moves from 2 to 1, you see it is moving from 2 to 1, then it is Ht1 minus Ht2 equal to K. So normal components means this is the relation B1 equal to Bn2, and the tangential component means Ht1 minus Ht2 equal to K. The condition is that if it is going from medium 2 to medium 1, medium 1 to 2, that will be different. So with this basic idea, now, so y component is a normal component, x and z component are the tangential component. This is the problem statement. To medium, H1 is given. So we have to determine the normal component, that is the component along y. We have to determine the tangential component, that is component along x and z. So first, to determine the normal component that is along that is basically the y component. So Bn2 means mu0 into mu2 into Hn2. What is Bn1? Bn1 equal to mu0 into mu1 into Hn1. mu0 cancel out. Now mu2 is given. mu2 is 4. So 4 into Hn2. What about mu1? mu1 is 2. Now what will be this Hn1? What is the Hn1? We have just mentioned that the normal component of the magnetic field means that is along y-axis. That is along y-axis means
Is the y coefficient?
Is 6 IY. This is the normal component of the magnetic field along y-axis. So that will be 2 into 6. So if you calculate it, the normal component of the magnetic field in medium 2, that will be equal to 3 into Iy. Next, you have to determine the tangential component. In the tangential component, there are two components. One is along x, another is along z. So one by one, we have to find out both these two components. So first, we will determine the tangential component. So in that case, the magnetic field is moving from 1 to 2. So what will be the equation? That will be Ht2 minus Ht1 equal to K. And first, we are considering the how we can determine the x component, the tangential component that is along x. So the basic equation from the boundary conditions, that is Ht2 minus Ht1 equal to K. We have to find out this Ht2 for the x component. So Ht2 equal to Ht1 plus K. Now Ht1, what will be this Ht1? That we will get from which one? From this H1. Now you are going to find out the tangential component that is along x or x component. So what is Ht1? That is nothing but this 4Ix. So Ht1 you can directly write down from the equation of H1. As we are considering it is the tangential component for the x component, so it will be 4Ix. Next is the crucial, how we can find out this K. To find out this K, basically you have to consider, you have to find out two parts. First, K will be equal to this Ht1 of K, perpendicular to Ht1 of K. Now you see equation of K is given. Now out of this, from this particular equation of K, you have to determine the tangential component for the x component. So you have to find out the perpendicular of Ht1 of K. Now perpendicular of Ht1 of K means you are concentrating on this x component. So which tangential component is now perpendicular to x? But there are two tangential components, x and z. First, you are going to find out the tangential component for the x. Clear? Now, in this particular solution, now you have to find out K. So you first consider the equation of K. K equal to 2Ix plus 4Iz. As you are concentrating on the x component, so this K will be equal to, first component will be perpendicular to the Ht1 of K. Perpendicular to Ht1 of K. The perpendicular of Ht1 to x is perpendicular. Which axis is the perpendicular to the x? That is nothing but z. So it will be 4Iz. It will be 4Iz. That's why it is 4Iz. Cross. Actually, just find out in that way. The K will be equal to dash cross dash. What will be that first dash? That is mentioned in this equation. That will be the perpendicular to Ht1 of K. Perpendicular, that will be perpendicular to Ht1 of K. Now you consider the equation of K. On this particular equation, you see which one is the perpendicular to the Ht1. As we are concentrated on the x component, so the perpendicular to x component means that is nothing but the z. So it will be 4Iz. 4Iz. 4Iz cap. Next, the cross product between the direction of propagation. What about the direction of propagation? the magnetic field is propagating in the direction of y. So it will be I y. Clear? Now in this particular situation, it is the cross product of Iz and Iy component. So as it is not in a sequence, if the cross product along x among x, y, z, they are in a sequence, then their cross product will be positive. That is, if you find out x cross y এর dot product cross product কি হবে? What will be the cross product of x cross y? That will be z. It is clear. Now it is whether it will be positive or negative. That depends on whether it is in sequence. If you find out x cross y, then it will be plus z direction. If you find out y cross x, then it will be minus z. This is the shortcut to remember it. Now if you find out y cross z, obviously it will be in the x direction. Now the question is whether it will be plus x or minus x. As this is the cross product in a sequence, so it will be in the plus x direction. So similarly, in that case, we are going to find out the z cross y, the cross product between z and y. So it should be x. It is clear. Now it is positive or negative. As z is coming before y, so it is not in a sequence, so it will be negative. That's why there is a sign. So it will be 4ix. This is the first term, 4ix, and 4iz cross iy. The cross product between iz and iy is nothing but ix. As they are not in sequence, so it will be minus. So it is 4ix minus 4iy. Sorry, 4ix minus 4ix. It becomes 0. If you have any doubt, you can ask me.
So no, sir.
Then in the next step, so till now we have find out the normal component, that is along y, that is basically the y component. Out of two tangential component, till now we have determined the tangential component along x, basically the x component of the tangential components. Next, the remaining part is the z components. So the tangential component for the z. So in the same process, ht2 minus ht1 equal to k. That means ht2 equal to ht1 plus k. Now what will be that ht1? Tell me how we can find out that ht1. Tell me what will be the ht1? The tangential component to the z. What is the tangential component to the z? There are two tangential components, one is x and z. Now when you are going to find out the tangential component for the z, that means the another one, that x is the tangential component. Okay. Now, so that will be 2iz. That will be 2iz. That thing. 2iz. So ht1 you will be able to write down directly from the equation of h1, as you are considering to find out the tangential component that is along z axis. So you have to concentrate on the z component of the h1. The z component of the h1 is nothing but 2iz, so it is 2iz. Now in same way, now you have to find out the k equal to, that will be the perpendicular to h1 with k. Perpendicular to h1 with k means
cross product
X.
Perpendicular with 2ix. This component 2ix.
cross ion cross product. sir.
Cross product of the direction of propagation. Direction of propagation, that is iy. Now what will be the
Iy.
ix? That is iz. Ix
Iz.
cross iz. Iy means iz. Then what will be this sign? It will be, it is positive or negative?
Positive.
As it is in
Positive.
sequence x to y, so it will be positive. So that is 2iz plus 2iz, that is total 4 of iz. So you see, we have find out the normal component of the magnetic field in the medium 2, that is 3 of iy. There are two tangential components. One is along x, one is along x, another is along z. Along x-axis it is 0, along z-axis it is 4iz. So what will be the final expression? That is H2 equal to, this x component is 0, x component is 0. Now what about y component? That is 3iy, 3iy. Next, what about the z component? Z component is 4iz. You should go through this particular example very carefully. It is very important to understand the magnetic boundary conditions. There is little bit tricky. That is how we can find out this K. Otherwise, the rest of the thing is very simple. That is similar with the boundary conditions related with the electric field also. May I proceed, or I have to explain more on this particular topic?
Sir, please explain one thing, sir, how to determine K.
To determine the K, you have to consider first the equation of the K. K is equal to 2ix plus 4iz. First, consider the basic equation of K. K equal to 2ix, that is given in the problem, 2ix plus 4iz. Now to determine the K for the tangential component, K will be the cross product of two elements. The first element is the perpendicular component, perpendicular to the corresponding magnetic field, perpendicular to the corresponding magnetic field, HT1, perpendicular to HT1 of K. Now, and what about the second component? That is very easy. That is the direction of propagation. The second one is the direction of propagation. I am shortly likhlam to direction of propagation. So the question is how to find out perpendicular to HT1 of K. That means in this particular expression of K, which one is perpendicular to the HT1? Which one is perpendicular to HT1? Now, for this particular HT1, you are going to find out which component, X or Z. So first we have determined the X component. X component. So for the X component, which particular component is perpendicular? When you are going to determine the X component, that means Z is the component which is perpendicular.
Z.
So what is the Z component in this particular K equation of K? That is 4iz. 4 into iz. Next term is clear. What is the direction of propagation? It is moving along y-axis. So it is iy. Now there is a cross product between iz and iy. As it is not in a sequence, so obviously the cross product between z and y will be x, because we are considering a orthogonal coordinate system between x, y, and z. So the cross
minus 6. It will be, sir, minus 6.
I am coming to that point. Z cross y, when it is not in a sequence, then it will be minus. So if you consider three coordinates, 3 axes in that way, so it is x, it is y, and it is z. Now if you say that this is y cross z, obviously it will goes to in the direction of x. The question is whether it is plus x or minus x.
So it is
that is in the x, but not in the plus x direction, rather it is in the minus x direction. That's why iz cross iy, that will be nothing but ix. That is mentioned in this particular step. Iz cross iy equal to ix, but there will be a negative sign. Similarly, in the second case, you see k equal to the cross product between two parameters. The first is the perpendicular to ht1 with k. In the second part, we are trying to find out the z component. So the perpendicular of this z component is nothing but the x component of k. The x component of k is 2ix. So it will be 2ix. And direction of propagation is iy. And obviously the ix cross iy is sorry. Ix cross iy will be iz as in sequence. So there will be no negative sign, it will be positive sign. Now is it clear?
yes, sir.
Yes, sir.
So I'm moving to the next part. That is Faraday's law. Actually, Faraday performed different experiments on the time varying, particularly on the time varying magnetic field. And it was his first, one of the observation that is, if you handle with the static magnetic field, that means if the magnetic field is static, it is not changing with time, there is no induced current in the circuit. So in case of static magnetic field, there is no question of induced current in the circuit. Is it clear? So Faraday has performed different experiments related to the static and time varying magnetic field. His one of the observation is that if you deal with the static magnetic field, there is no question of induced current in the circuit. But when it comes about the time varying magnetic field, time varying magnetic field means that is changing with time. So if there is any change in magnetic field or the variation in the magnetic field with respect to time, so there must be a current there must be some current will be induced in the circuit. Okay, there must be some current that will be induced in the circuit. So depending on these two observations on the on his experiments on the magnetic field and the static magnetic field and time varying magnetic field, states that the rate of change of magnetic flux with respect to time that will generate the induced EMF in the circuit. That is, if we consider a time varying magnetic field, that means the change in magnetic flux with respect to time, it will generate the induced electromotive force EMF that will basically induce the current in the circuit. Okay, so that is the observation of Faraday's law. That means how we can represent it mathematically. Rate of change of magnetic flux, that is d phi b dt. Change in magnetic flux will induce the electromotive force. So we can write this V of EMF, potential due to the electromotive force, that will be equal to minus of d phi b dt. What is phi b? Phi b is the magnetic flux. D phi b dt means rate of change of the magnetic flux. So this negative sign is basically due to the induced EMF and time varying field, they are in the opposite direction. Induced EMF and the time varying field, they are in the opposite direction. That's why this negative sign is considered. So that is the equation of electromotive force from the Faraday's law. Now from the basic idea on the potential, now if we write the equation of VEMF as per our concept on the potential, what is the equation of VEMF? VEMF will be integration of E dot dl, that is known to us, that is E dot dl, integration of E dot dl, that will create the induced electromotive force, that is VEMF equal to, what is V of EMF? That is potential due to electromotive force. Now this is also the potential due to electromotive force, but that potential due to electromotive force is basically generated due to the change in magnetic flux, and that is the mathematical description of the Faraday's law. Faraday states that rate of change of magnetic flux will induce the electromotive force in the circuit. So due to the induced electromotive force in the circuit, there will be potential. So potential due to electromotive force, that will be equal to minus of d phi b dt. Now from the basic concept of the potential, what will be the potential due to electromotive force? That will be equal to E dot dl. So this is the equation of potential due to electromotive force, which is generated by the change in magnetic flux. This is the equation of potential due to electromotive force, while electromotive force is due to the electric field. So two is different. One is generating from the changing magnetic flux, one is generating from the electric field. So in that case, we are considering the positive sign, because in that case, we are considering that work done is done on the charges. Work is not done by the charge, rather work has been done on the charges. So we are considering that this is a positive sign. So B of EMF equal to integration of E dot dl. So now from this Faraday's law, so this Faraday's law is basically describing the induced electromagnetic force in the circuit due to change in magnetic flux. Change in magnetic flux means we are considering the time varying magnetic field. We are considering the time varying magnetic field. So this Faraday's law basically deals with the time varying magnetic field, where he states that for a time varying magnetic field, there must be some induced current in the circuit, and as per this statement, the rate of change of the magnetic flux with respect to time, that will induce the electromotive force in the circuit. So what will be the V of EMF? That is equal to minus of d phi v dt. Now we are comparing this with our basic knowledge of the potential from the electric field point of view. From the electric field point of view, we know that what will be the potential due to the electromotive force, that will be equal to integration of E dot dl. Now if you compare these two equations, equation 1 and 2, we can write down that integration of E dot dl equal to minus d phi v dt. Basically, when we compare these two equations, we will get the Maxwell's equation for time varying magnetic field. Okay. So now we are comparing these two equations, equation 1 and 2. Once we compare these two equations, we have find out that E dot dl equal to minus d phi v dt. Where this phi b, I have already mentioned, this is nothing but the magnetic flux. We have already knowledge on the magnetic flux. Magnetic flux means that is the integration of B dot ds. So if you put that in this particular equation, it becomes integration of E dot dl equal to minus of d dt of integration over B dot ds. So this particular equation A, or in this particular simplest form, this is known as the integral form of Maxwell's equations for the time varying magnetic field. E dot dl line integral, that is on the closed loop, it represents, this particular sign represents the closed loop, line integral of the closed loop. E dot dl equal to minus of del v del t dot ds. So this is the integral form of Maxwell's equation for the time varying magnetic field. Now we have to find out the differential form for this from this integral form. So obviously there is a time line integral, on the right hand side there is a surface integral. So to convert the line integral into surface integral, what particular theorems we have to apply? You have to apply the Stokes theorem. That point you should keep in your mind. When you are converting from line integral to surface integral, you have to apply the Stokes theorem. When you are considering from surface integral to volume integral, you have to apply the Gauss's theorem. These are the main things. Once you got the integral from the basic laws, basic laws means either your all the Maxwell's equations, either it is coming from the Gauss's law, Faraday's law, or Ampere's law. So first you will get in integral form. Once you got the integral form, then you apply the proper theorem, either Stokes theorem or Gauss's theorem, or that is divergence theorem. So it is in line integral to surface integral. So we have to consider the application of Stokes theorem. So if you apply the Stokes theorem, it will be on the left hand side, it becomes curl E dot ds, that is equal to minus del v del t ds. So on the both side of this equation there is a surface integral, so we can cancel out this integration sign. So ultimately it becomes curl of E equal to minus del v del t. Previously, for the static magnetic field, if you remember that curl E was 0. So this equation A, that is the Maxwell's equation for time varying magnetic field in integral form, and equation B is the the Maxwell's equations in differential form for the time varying magnetic field, and its corresponding equation for the static magnetic field, that was equal to nothing but curl E equal to 0. So curl E equal to 0, that equation we have already derived previously for the static magnetic field, static field, that was 0. What is the significance of this curl E equal to 0? What is the significance of curl E equal to 0? What is the significance? So it describes the conservativeness of electric field. Curl E equal to 0. So it describes the conservativeness of electric field. Or you can say from the basic integral form, E dot dl equal to 0. For the, it will be E dot dl equal to 0 for the static magnetic field. So it basically describes that for a closed path, the potential will be 0. Now from this new equation, what will be your conclusion? From the new equation, what will be your conclusion? That we have already mentioned, that is basically the Faraday's law. Change in magnetic flux will induce the potential. So this is the derivation of Maxwell's equation for the time varying magnetic field, and it describes that curl E equal to minus del v del t. If there is any change in magnetic flux, that will induce the electric field. Okay. So this particular Maxwell's equations is very important because it describes the relation between the electric field and magnetic field. Change in magnetic field. This particular relation says that change in magnetic flux, if there is a change in magnetic flux, that will induce the electric field. Is there any doubt?
No, sir.
Okay, then I'm moving to the another part. That application part I have to mention. Okay, so as I mentioned, this particular laws that is coming from the Faraday's law, this is very important, particularly in different applications like transformer and ammeters. This particular law is follows to prepare the transformer, ammeter, and so many things. So in transformer, what happens? There is a primary winding, there is a secondary winding. In the primary winding, you are applying some current, AC input, and on the secondary winding, what happens? There will be induced current on the secondary windings. So you are applying something in the primary, the same thing will be induced in the secondary windings. So that is nothing but the application of laws of the Faraday's law, or you can say the Maxwell's law. Similarly, in case of ammeter, in ammeter, there is a coil when you are applying some current. Due to this induced current, that indicator of the galvanometer or the indicator of this ammeter will deflect. So all these things are basically the applications of Faraday's law that describes that if there is a change in magnetic flux, electric field will that will induce the electric current. There are so many applications, but for the sake of simplicity, we have just mentioned these two applications because in our different syllabus, you have to deal with this transformer and ammeter also. So all these are basically designed depending on the Faraday's law, or you can say the Maxwell's law for the time varying magnetic field. So the next we have to consider the equation of continuity for time varying field. We are familiar with the equation of continuity for the static field. Now you have to consider the this particular continuity equation for the time varying fields. Now, if we consider a closed surface enclosing a particular charge, then what will be the total outward flow of the current that we can describe by these equations? If we consider a closed surface that enclosing a particular charge Q, if we consider a closed surface enclosing a charge Q, then what will be the outward flow of the current? Outward flow of the current that is equal to surface integral of J dot ds. What is J? J is the surface current density, we know. So this is the equation of continuity in the integral form. Now if we consider the conservation of charges, J dot ds. Now if we write down the equation of current in terms of charge, so I is nothing but minus dq dt. I is nothing but minus dq dt, where this dq dt is the rate of decrease of charge. When this charge is leaving this particular surface, then only we will get the current. So this minus dq dt is representing the rate of decrease of charge. That's why negative sign is considered. Now, if you compare these two equations, you see that it is I equal to z dot ds, it is I equal to minus dq dt. Now, if we consider this surface integral to volume integral, surface integral to volume integral means that is nothing but we have to apply the divergence theorem. So, j dot ds equal to divergence of j dv. So, thus, if we compare this, if we combine these three equations, we can write down that this divergence of j dv, or this particular integral, that is volume integral of divergence of j dv, that is equal to minus dq dt. Okay. Now, by definition, if we represent this charge, total charge, how we can find out the total charge? From the volume charge density, that is the volume integral of rho v dv, where rho, what is rho v? Rho v is the volume charge density. So, from these equations, we can write down that this divergence of j dv equal to minus dq dt. Q is rho v, so it is integration of d rho v del t dv. Now, this particular term, that is d dt of rho v, this is nothing but a rho v dot. So, now on the both side of this equation, there is a volume integral. So, we can write down that divergence of j equal to minus of rho v dot. And this particular equation is known as the continuity equation in differential form or point form. So, divergence of j equal to minus rho v dot, or you can say del rho v del t. Okay. So, next we are moving to the Maxwell's equation, that is based on Ampere's circuit law for time varying magnetic field. So, with the basic idea on this continuity equation, I think this equation is familiar to you. Curl of H equal to J. We have already, this is the differential form of the Maxwell's equations for the static field, not for the time varying field. That is for static electromagnetic fields. If we consider this Maxwell's equation, curl H equal to J, that is the Maxwell's equation in differential form for the static field. Now we know that if we take this divergence of curl H, that is divergence of curl of any vector, that is from the basic vector property of the vector field. Divergence of the curl of any vector field is always 0. So, if you apply the divergence on this equation 1 on the both side, that is divergence of curl of H, that is equal to divergence of J, that is equal to 0. So, we find out that from this equation 2, what we find out? Divergence of J equal to 0. But just from the equation of continuity of current equation, what we have find out? However, from the continuity of current equation, it requires that divergence of J, that is the equation of continuity equation, if you have to maintain in the continuity in the current, divergence of J will be equal to minus del rho v del t for the time varying fields. So, it should not be 0. So, there must be some fallacy. So, when we are dealing with the Maxwell's equations of the static electromagnetic field, we have seen that curl A is equal to 0. Now, we are taking divergence on the both hand side. And once we take the divergence on the both side, we have seen that divergence of J equal to 0. But just in the previous slide, when we have discussed about the continuity equation, we have seen that divergence of J equal to minus del rho v del t. So there is some disparity between these two equations. One is saying that divergence of J equal to 0, another thing is saying that divergence of J equal to minus del rho v del t. So obviously there is some fallacy between these two equations. Now this equation 2 and 3 becomes incompatible for the time varying field. So obviously it will become incompatible because this equation 2, it is for the static field, whereas this equation 3, this is basically for the time varying field. That's why this type of incompatibility we are observing. So to overcome this incompatibility between these two equations, what we can do, that we are adding one term purposefully. To overcome the incompatibility between equation 2 and 3, we are now modifying the equation 3. Sorry, we are now modifying this basic Maxwell's equation for the static magnetic field, that is curl H equal to J, by adding one extra term. Now once again we will apply the same process, that is we will take divergence on the both sides. Okay, this JD, that is purposefully added with the basic Maxwell's equations, that is known as the displacement current density. We will discuss in detail about this displacement current and displacement current density. For the time being, we just considering that we have added some extra term, that is known as JD, where JD equal to del T, that is known as the displacement current density. Now in the same way, if we take divergence on the both side of this equation 4, divergence of curl of H, so as per the basic vectors law, it will 0. On the right hand side, it is nothing but divergence of J equal to 0, that is divergence of, sorry, on the right hand side it becomes divergence of J and divergence of JD. So if divergence of J plus divergence of JD equal to 0, that means we can write down that what will be the relation between divergence of JD and divergence of J, that is divergence of JD equal to divergence of J. Now as per the continuity equation that is mentioned in this equation 3, what is divergence of J? Divergence of J equal to minus del rho v del T. So now in place of this divergence of J, if we put del rho v del T, it becomes minus minus plus, so it becomes del rho v del T. So this divergence of JD equal to, it becomes del rho v del T. This del rho v del T is nothing but d dt of divergence of D. So it basically written as divergence of del D del T. So to make these equations 2 and 3, which are basically, one is from static, for the one is for the static field and another is for the time varying field. In order to make them compatible, we have added one extra term with the Maxwell's equations, that is curl H equal to J plus JD, where JD is the displacement current density. And when we are applying the divergence on the both sides of these equations, we have seen that this divergence of JD equal to minus of divergence of J. Now minus of divergence of J means from the current continuity equations, it becomes del rho v del T. So this del rho v del T is nothing but this divergence of del D del T. So finally, is equal to, since this JD equal to basically the del D del T, the differential change in the electric field intensity D. So these equations, the Maxwell's equations for the static magnetic field was curl H equal to J to become To find out the compatibility between the static and static field and the time varying field, we have considered curl H equal to J plus ZD, and applying that current continuity equation, we have find out that this JD equal to del T del T, JD equal to del T del T, we have find out by applying the current continuity equation. So the Maxwell's equations becomes or modified as curl H equal to J plus del T del T. Previously it was only J, but now this term, this del T term, due to the time varying field. So for the static field, the Maxwell's equations only curl H equal to J. But for the time varying magnetic field, this curl H becomes J plus del T del T. That is, J is representing the conduction current and this del T is representing the displacement current. So that is the Maxwell's equation derivations for the time varying magnetic field. It is basically based on the Ampere's circuit law. This Ampere's circuit law easily describes the static field, but it fails to describe for the time varying magnetic field. That's why Maxwell's include this particular modification. This modification of JD is basically from the Maxwell's part. This JD was included by the Maxwell's to overcome the fallacy or the, you can say, the drawback of the Ampere's law. That's why this particular law is also known as Ampere-Maxwell's law. Now, as I mentioned, we have to discuss in detail about this displacement current density. So in the next part, we are going to discuss about this particular point. Now, on this particular point, if you have any doubt, you can ask me. Otherwise, I will move to the next part.
No, sir.
And summarizing, we have first described the current continuity equation for the time varying fields. Then we have started with the Maxwell's equations that we have got from the Ampere circuit law for the static field. That is nothing but curl H equal to J. Now on the both side, we have applied the divergence from the basic law of vector law. That is divergence of curl of any vector that must be 0. So it says that divergence of J equal to 0. But from the current continuity equation, we have just seen that divergence of J equal to minus del rho v del T. So there is an incompatibility between these two equations. To overcome this incompatibility with the basic Maxwell's equations for the static field, we have added, or Maxwell's basically include these modifications along with the conduction current density J. JD is included. Now this JD is calculated or find out what is basically this JD. That is by applying, once again we are applying the divergence on the both side, and we have seen that divergence of JD equal to minus of divergence of J. Now divergence of J we have from the current continuity equation, it is del rho v del T. So it is basically divergence of JD equal to del rho v del T, and that is equal to divergence of del T of divergence of D, that is gradient of del T. So this JD, that is the differential displacement current density, JD equal to nothing but the del T. So the Maxwell's equation becomes curl H equal to J plus del T. So the next point is that what is this displacement current? Why Maxwell's needs to include this particular modification in the Ampere's law? What was the fallacy with the Ampere's circuit law that has been overcome by the Maxwell's inclusion? So to describe about the displacement current, so it's basically the Ampere's law that did not able to describe the some situations, particularly for the time varying fields. As per the Ampere's circuit law, it says that if we consider a closed surface, the current enclosed by this closed surface, that will be equal to the total induced magnetic field. That is integration of B dot dl equal to mu 0 into I enclosed. That is the Ampere's circuit law that we know. If we consider a closed surface, then the total induced magnetic field, that is B dot dl, that will be equal to the total current enclosed by the loop. That is the Ampere's circuit law, and it is for the static magnetic fields basically. Now we'll consider what will be the problem to demonstrate this particular situation with the help of Maxwell's equations. Now with this particular conductor, we are connecting a charging or discharging capacitor. So this is basically a plate capacitor. This two plate is representing the two plates of the parallel capacitor. This is the current through this particular conductor. Now, as per the Ampere's law, if we consider a closed loop around this particular conductor, we can describe the magnetic field at this particular point P by this equation. Okay, because there is some current enclosed by this loop. What is clear? When we are going to apply the Ampere's law at this particular point over the conductor where current is moving from left to right and this current is I and C. So at this particular point, at this particular arbitrary point P, we can describe the magnetic field by this Ampere's law. But now if we consider any closed surface in between this parallel capacitor, if we consider any surface, closed surface in between these two parallel plate of the capacitor, then the question is what will be the magnetic field at this particular point. As per the Ampere's law, there will be any magnetic field. Try to answer it. Ampere's law says that if we consider a closed surface surrounding a current carrying conductor, the total magnetic field, that is integration of B dot dl, that will be equal to the total current enclosed by the surface. Okay.
Yes.
So by applying the same concept, will it be possible to find out the magnetic field over this particular point K, where we are considering this particular loop or surface in between the two plates of the parallel capacitor? Try to answer it.
Sir, there will be.
We have learned about the Ampere's law in details. I have again summarized it. So as per the Ampere's law, if we consider a closed loop around this particular conductor at point P, we can describe the magnetic field by this equation or Ampere's law. It will follow the Ampere's law. But the situation is that on the end of the conductor, we have considered a capacitor, parallel plate capacitor. Obviously, there is some gap between these two plates. And in between this gap, if we consider another surface, and at this particular point K or any arbitrary point on this particular surface, what will be the magnetic field? Basically, is it possible to find out with the help of Ampere's law?
No.
Why? Why? Simple answer, because there is no current.
Because magnetic field. Yes, sir.
Because there is no current enclosed by the surface. Is there any current enclosed by the surface? No. Then the direct answer will be that we will not be able to find out the magnetic field on this particular point Q because there is no current enclosed by the surface. So as per the Ampere's law, there is no magnetic field. So if we consider the magnetic field or magnetic flux density B at point Q, it will be 0. But if you perform the experiment, you will see that this magnetic flux density BQ that is at point Q, that will not be 0. That is the fallacy of this Ampere circuit law. It cannot explain the
But
induced
sir,
magnetic field. Yes.
there will be a displacement current when we are trying to
That's why I'm trying to explain you. I know in class 12 also you have learned about this particular point. Still, I'm going to discuss it for your benefit. So, as per the Ampere's law, you can't say that there is a magnetic field. But when you will perform some experiment, you will see that there is some magnetic field. And that magnetic field is quite equal to the magnetic field at point P. So experiment says that if you perform an experiment and you try to find out the magnetic field at point Q, it will be quite equal to the magnetic field at point P. So as per the Ampere's law, if you apply the Ampere's law directly for this particular situation, or to find out the magnetic field in between the parallel plate capacitor, it will be 0. But it is not actually true. If you perform experiment, it will be quite similar or equal to the magnetic field at point P. Now the question is, why this magnetic field at point Q will be equal to the magnetic field at point P? You can't answer it directly by saying that it is due to the displacement current. You have to explain it. So first we have to find out what are the source of electric field. What are the source of electric field? That is, we know that is due to the charges. Second, that is due to the change in magnetic flux as per the Faraday's law. Okay, so we know that electric field will be induced due to, or there will be some electric field if there are charges. If there is any change in the magnetic flux, electric field will induced. So these are the two main sources of the electric field. Now what about because we are going to find out the magnetic field by applying the Ampere's law at point P and at point Q. Now, what about the source of magnetic field? As per the Ampere's law,
Current.
it is only the current. It is only the current. Charges is not responsible for the magnetic field. So what else that is responsible for the magnetic field? Basically, when we are considering parallel plate capacitor and this current carrying conductor is connected with this parallel plate capacitor, you have to consider the charge distribution on both the plates. So depending on the charge distribution, we can easily draw the electric field lines in between the two parallel plates. Now, if there is any change in magnetic field or in this particular current, suppose this current is increasing or decreasing. Current is increasing means this parallel plate is charging. So there will be change in the electric field intensity. And due to this change in electric field, due to the change in current, so this is the second parameter which is responsible for the generation of magnetic field. That is the electric flux, change in electric flux. When you are increasing the current, this electric flux in between the parallel plates are changing. Is it clear? When you are increasing the current due to the charging and discharging of the parallel plates, the electric flux in between these two parallel plates will change. And due to this electric change in plates, electric flux is changing with respect to time. So obviously that electric flux is responsible to show the magnetic field at point Q that you have observed in the experiment. But that cannot explain with the help of this simple Ampere's law. Clear? So once we have seen that this Ampere's law is not valid for this type of surface in between the parallel plates, and we have seen that it is basically due to the change in electric flux with respect to time. So this change in electric flux with respect to time is another source of magnetic field. So as there is a change in electric flux with respect to time, it is producing the magnetic field which is observed in the experiment. So what will be the modification in this Ampere's law now? So depending on this inclusion of this electric flux density or electric flux with respect to time, now we have to modify this Ampere's law. That has been done by the Maxwell's. Okay. So B dot dl equal to mu 0 into I enclosed, that remains same. Now we are including, basically rather than Maxwell's included this particular term, which is basically the due to the change in electric flux with respect to time, d phi e dt. As there is change in electric flux with respect to time, that will induce the magnetic field. So once we consider this Ampere's law plus this inclusion of the electric flux with respect to time, then we can explain any situations, whether it is out of the parallel plate capacitor or in between the parallel plate capacitor. And that modification has been done by the Maxwell's. So this particular kind, now the question is, what will be the unit of this particular parameter or the second term? What will be the unit of the second term?
As this a unit of the current.
Yes, because both are in the same, within same bracket, so obviously they will represent the same unit. As I is the current, so it will also will be like current, but not like the conduction current. So the first term is basically representing the conduction current that we are familiar due to the flow of charges. Now the second term is basically, it is known as the displacement current. It is not like real current like conduction current. Still, its function is like current. So it's known as the displacement current, and it is basically due to the change in electric flux with respect to time. So this particular equation is modified with this particular, this is basically the final form, mu 0 into I is representing the conduction current, and this term is representing the ID, it's representing the displacement current. So this equation is known as Ampere-Maxwell's law. Clear? So Ampere's law, Ampere circuit law is not able to explain the existence of displacement current or the generation of magnetic field due to change in electric flux. So this particular modification has been done in the Maxwell's equation for the time varying magnetic field that we have already discussed, that is curl H equal to J plus JD. For the static magnetic field, it was curl H equal to J, but once we consider the time varying magnetic field, so we have to include the displacement current, so it becomes curl H equal to J plus JD, and it's basically the modifications of the Ampere circuit law by the Maxwell's, and it becomes the Ampere-Maxwell's law. So this displacement current, the current that is the normal current or conduction current, it basically arises due to the flow of charges in the conductor, whereas this displacement current is arises due to the change in electric flux or electric field inside the plate of the capacitor that we have discussed right now. Displacement current arises due to the changing electric field inside the plate of the capacitor. So this displacement current is not a real current in the sense of where we are describing the conduction current. However, it acts like the real current. That's why it is known as the displacement current. So whenever we will consider the change in electric field, we can consider the existence of displacement current. So the source of magnetic field, another source of magnetic field is the change in electric field or the rate of change of the electric flux. So that's all about the displacement current. We one by one we have find out all the Maxwell's equations. So this is the summary table for the Maxwell's equation for time varying fields. For the time varying fields, these two equations remains same. Divergence of D equal to rho V, that it basically comes from the Gauss's law. Divergence of B equal to 0, that is basically the non-existence of isolated magnetic monopole. This curl H, it is for the static magnetic field, it is basically 0, curl equal to 0. But once we consider the Faraday's law for the time varying magnetic field, it becomes curl equal to minus del B del T. Similarly, from the basic Ampere's law, we got curl H equal to J. But once we include the modification done by the Maxwell's due to the electric flux, changing in electric flux, we have to include the term that is the displacement current. So this curl H becomes curl H equal to J. That particular equation is modified by curl H equal to plus del D del T, where this del D del T is basically the displacement current density. Now I have summarized.
Displacement current is also dependent on.
Yes, tell me.
Displacement currents also depends on electric medium. Yes.
Yes, almost that's also true. In that equation, JD equal to del D del T. Del D del T means epsilon D. D equal to epsilon D. Epsilon is the permittivity. Okay, so it also depends on the dielectric medium also. If we summarize all these Maxwell's equations that we have derived so far, whether it is for static field or magnetic field, first we have started with the Gauss's law for the electric field. We have considered the Gauss's law for electric field. So once you consider the Gauss's law, that means E dot ds equal to q by epsilon. That is the total charge enclosed by the corresponding surface. That will be the total electric field. From the integral form, how we can convert it into the differential form, that is known to us. It is surface integral to volume integral. So you have to apply the divergence theorem. And this is basically integral form, and this is the differential form or point form. So what will be your remark from this first law that comes from the Gauss's law for electric field? Divergence of D equal to rho V, existence of electric flux. Electric flux will only exist if charge is enclosed. If the charge is not enclosed by the surface, then there is no question of electric flux. That is the main point of the first law of the Maxwell's, or that is basically comes from the Gauss's law. If the charge is enclosed by the surface, then the electric flux will exist. So existence of electric flux only if the charge is enclosed by the corresponding closed surface. That is, if you consider a closed surface, and there is no charge inside this particular surface, then there is no question of electric flux. Now the second one we have derived from the point of view of electrostatic potential. From the point of view of electrostatic potential, we have derived the for non-time varying field. NTV is representing the non-time varying field. For the non-time varying field, we have find out that E dot dl equal to 0. That is nothing but curl E equal to 0. E dot dl equal to 0 means that is for a closed path, the potential difference will be 0, and curl E equal to 0 means that is the conservativeness of the electrostatic field. Now, when we have included the Faraday's law for the time varying field, it becomes E dot dl equal to minus d phi dt, change in flux. It is better to write d phi b dt. It will be d phi b dt, change in magnetic flux. E dot dl equal to minus of d phi b dt. That will be minus of d phi. You should note it, okay? It will be d phi b dt. So this particular law basically says that if there is a change in magnetic flux, it will induce the potential. Change in magnetic flux will induce the potential. Same thing from the differential form, curl E equal to minus del B del T. Change in magnetic flux will induce the potential. So this is basically the time varying field. This equation is basically for the time varying fields. Now, the third equation of the Maxwell's, that was basically derived from the Ampere circuit law for the non-time varying field. Non-time varying field, it was H dot dl equal to, that is J dot ds, and we have find out that is curl H equal to J. So curl H equal to J means that is not equal to 0. Not equal to 0 means magnetic field is not conservative in nature. Okay. Now we have right now in today's class we have discussed what was the fallacy with the Ampere circuit law for the time varying field, and we have come up with the Ampere Maxwell's law. In Ampere's Maxwell's law, we have to consider the existence of displacement current due to the change in electric flux density. So this particularly describes the change in electric flux with respect to time will induces the magnetic field. So this is basically the second one is basically the for the time varying. This second one is basically the Maxwell's third equation for the time varying field. So you can count in that way. This is the Maxwell's first equation that comes from the Gauss's law. Maxwell's second equation, it comes from the electrostatic potential, that is for non-time varying field. For the time varying field, we have to consider the Faraday's law. Maxwell's third equation, it comes from the Ampere circuit law for the non-time varying field. But when we will deal with the time varying field, we have to consider the modified version of the Ampere circuit law, that is Ampere's Maxwell's law. And finally, the Maxwell's fourth equations, that basically comes from the Gauss's law for magnetic field. The first law comes from the Gauss's law for electric field. The last law basically from the Gauss's law for magnetic field, and states that B dot ds equal to 0, that is the integral form. From the integral form, we can convert into the differential form, that is divergence of B equal to 0. So divergence of B equal to 0 means, so if you remark from the first B dot ds, that is magnetic flux densities. Magnetic flux density is conservative in nature as divergence of B equal to 0. So the magnetic flux is conservative in nature. And second one is that isolated magnetic charge does not exist. That means non-existence of magnetic monopole. It says the non-existence of magnetic monopole. So we have discussed all the four equations, whether it is time varying for the time varying field or for the non-time varying field, and the corresponding associated law, Gauss's law, Faraday's law, Ampere circuit law. Faraday's law, and as well as we have discussed all the boundary conditions for electric field and magnetic field. So this is the end of this particular module or part. In the next class, probably that will be my last class for this semester, I'll discuss about the wave propagation and then the related topics like Poynting's theorem, etc.
Okay, sir.
Okay, so at the end of the class, I will share the presentation. You should go through the presentation immediately so that you can cope up with the class.
Sir, what will be the syllabus for the second internal exam?
Up to today's class.
Okay, sir.
I recently heard that you did not able to even say the Maxwell's equations. I have discussed all the equations step by steps, how we are starting from the basic background, then we have derived the corresponding Maxwell's equations for time varying as well as for the non-time varying magnetic fields. Still, you did not able to just tell the Maxwell's equations. Anyway, it's my duty to explain everything in details. At the same time, I am sharing all the presentations without any hesitation. Still, you are not going through the PPTs, probably. Is there any problem to understand my classes?
Sir, there is no problem, sir, but I don't know when we know the Maxwell equations. But
Someone told me they asked you about the Maxwell's equation, but you did not able to answer.
previous calls, maybe it's DG sir asking about Maxwell equation, and I am trying to explain that, but I was not properly audible, so sir stopped me in that time. Maybe
Anyway, it's my
that
expectation
time.
that you should at least explain the basic of Maxwell's equation and their significance. That's why I have summarized all the Maxwell's equation in my last slide. And from that particular table, you can find out the clue how to start to derive all the Maxwell's equations. That's why in the first column, I have write down the background. So that is the clue where you have to start to derive the corresponding Maxwell's equations. In the last column, I have mentioned the significance of each and every Maxwell's equations. Anyway, I am trying my level best. Now it's your duty to deliver the proper answers if someone asks.
Sir, actually, DG sir asked about the Maxwell equation around 3 weeks ago, and we have studied it 2 weeks ago, so there might be a miscommunication.
Then you should mention that till now we did not.
Yes, sir, we had
write about
mentioned
the
that.
Maxwell's equations.
Yes, sir, we had mentioned this.
But sir, in that particular time, sir, I know the Maxwell equation. I was trying to explain, DG sir, what is the Maxwell equation, but that particular time, sir can't hear me. So sir stopped me at that time. Maybe that's why sir was complaining about us.
Anyway, hope when the next time if anyone asks you, you should at least explain the Maxwell's equations properly.
Sure, sir.
Abhishek Kumar Mahato.
Present, sir.
Next, Alamgir Shapui.
Present, sir.
Alamgir Anirban. Anirban Noskor. Absent or present? Archana Kumari.
Absent, sir.
Present.
Okay, Arijit Chakraborty. Who's trying to admit now? Gaurango Das. Arijit, yes बोल रहे ना present. Orko.
Present, sir.
Orko Prabhu.
Present, sir.
Sir, Gauranga Das.
এখনো অ্যাটেন্ড তোমার পর্যন্ত আসেনি ওয়েট অর্ণব বড়ুয়া
Present, sir.
দীপ কুমার
Present, sir.
গৌরাঙ্গ প্রেজেন্ট
Present, sir.
গৌরাঙ্গ ইউ আর অ্যাবসেন্ট ইন লাস্ট টু ক্লাসেস
স্যার আমার মোবাইলে নেট শেষ হয়ে গেছিল তাই অ্যাটেন্ড করতে পারিনি
পরপর দুদিন মিন্স ওয়ান
স্যার ওই দুদিন 5টা করে ক্লাস থাকে তো সারাদিন তো মোবাইলের নেটে ক্লাসগুলো অ্যাটেন্ড করা সম্ভব হয়নি
নেক্সট শাহানা
Present,
রায়
sir.
সায়ন
Sir, present.
ওকে সায়ন
Present, sir. Present, sir.
সায়ন নদী প্রেজেন্ট
Present, sir.
শ্রাবণী
Present, sir.
শাশ্বত
Present, sir.
সৌভিক চ্যাটার্জি কে অ্যাবসেন্ট ইয়ে লিখেছে তো প্রেজেন্ট সৌভিক চ্যাটার্জি সৌরদীপ দাস
Present, sir.
স্বস্তিক কুমার ঘোষ অ্যাবসেন্ট
Absent.
নেক্সট তর্পণ প্রেজেন্ট দেখলাম না তর্পণ বর্মন অ্যাবসেন্ট তুহিন
Present, sir.
রূপকুমার
Sir, Shovik present.
সৌভিককে প্রেজেন্ট দিলাম যে
Oh,
রূপকুমার বিশ্বাস অ্যাবসেন্ট ঐন্দ্রিলা চ্যাটার্জি
Present, sir.
প্রেজেন্ট নেক্সট শুভম কুমার গুপ্তা
Present, sir.
প্রেজেন্ট শ্রীধর সামন্ত
Present, sir.
প্রেজেন্ট শেখ মাসিবুল ইসলাম অ্যাবসেন্ট নেক্সট অর্ঘ্য প্রেজেন্ট আর অ্যাবসেন্ট অর্ঘ্য অধিকারী
Sir, absent, sir.
রনিত মিশ্রা absent।
নেই স্যার
এটা ক্লাস করলো কি না করলো এদের কাছে ক্লাস নোটস গুলো চলে যাচ্ছে উদয় সানিগ্রাহী
ইয়েস স্যার
প্রেজেন্ট উদয়ন মন্ডল উদয়ন
yes, sir. Yes, sir. Present.
রাহুল অ্যাবসেন্ট মৃণাল রজক অ্যাবসেন্ট সম্প্রীতি
Present, sir.
অপর্বিতা,
Present, sir.
আচ্ছা, আর কেউ নতুন নেই তো আবার আজকে?
হ্যালো স্যার,
না স্যার।
হ্যাঁ,
হ্যালো স্যার।
আমি শুনতে পাচ্ছি, বলো।
হ্যাঁ স্যার, আমার স্যার মাঝে মাঝে আমার স্যার ক্লাস অ্যাবসেন্ট হয়ে যায়। আসলে অ্যাকচুয়ালি স্যার আমাকে বাড়ির বাইরে গিয়ে ক্লাস করতে হয়, তো তার জন্য স্যার আপনি স্যার নোটসগুলো স্যার প্লিজ দেবেন, মানে আমি ওটা দেখি আর কি।
তুমি কে বলছো বলো?
স্যার আমি উদয়।
নোটস গুলো দেবেন মানে আমি তো যে আমার কাছে যে মেইল আইডি গুলো আছে সেখানে পাঠিয়ে দিচ্ছি তো।
হ্যাঁ স্যার ওইগুলোই আর কি, না আমি বলছি। হ্যাঁ, তার জন্য স্যার মাঝে মাঝে ক্লাস মিস হয়ে যায় আমার আর কি।
তোমার তো ক্লাস মিস দেখলাম না, তুমি তো সবই মোটামুটি
একটা অ্যাবসেন্ট আছে স্যার, দেখুন অ্যাবসেন্ট আছে।
আচ্ছা আমি দেখে নেবো। যাই হোক, আমি তো সবাইকেই তো যে অ্যাক্টিভ মেল আইডি বলে আমার কাছে যে লিস্টটা পাঠিয়ে রেখেছে তোমরা, আমি সেখানেই পাঠিয়ে দিই।
স্যার,
হুম,
স্যার আমি আমার মেল আইডিটা পাঠিয়ে দিয়েছি আপনাকে।
আচ্ছা ঠিক আছে, আমি নোট করে নিচ্ছি। আজকের নোটটা তো আমি পাঠিয়ে দিচ্ছি, বাকিগুলো তুমি ওদের থেকে কালেক্ট করে নিও, ঠিক আছে?
ওকে স্যার।
ওকে, ঠিক আছে, আমি লিভ করলাম। আচ্ছা, নেক্সট ক্লাস মানে হচ্ছে তো নেক্সট উইকে তো পরীক্ষা, 3 তারিখে পরীক্ষা।
হ্যাঁ স্যার।
তাহলে 7 তারিখ,
হ্যাঁ,
3 সাথে 10 তারিখ মোস্ট প্রবলি আমি একটা পাবো। 14 তারিখ অবধি তোমাদের ক্লাস হওয়ার কথা।
Yes, sir.
14 তারিখে আমি ওয়েব প্রোপাগেশনটা যতটা পারি আমি যেটুকু দরকার সেটুকু আমি কমপ্লিট করে দিতে পারবো আশা করি, ঠিক আছে?
Okay, sir.
আচ্ছা স্যার,
ওকে।
থ্যাংক ইউ স্যার।